files, and then I go to source, VUT, chem, mold draw, data, reserpine, molecules. Okay, but how do I view this? What is a mole file? Because I'm wondering if is there and maybe I should have a better understanding of the different file formats of chemistry in general, because I want to. Okay, so here's the project right now. Basically, I'm going through the R.B. Woodward total synthesis of reserpine, and I'm manually drawing every intermediate in Catcher, and I'm saving the .ket Catcher file, and I'm saving the I think it's called mole V3000 or something like that. I don't know what it's called, but the 3000 one. And what I'm wondering is, like, I've been downloading them, but how do I view them? Because it's just an ASCII file. Is this right? This really doesn't look right. How do I fucking download it? What the hell? What? Okay. All right, good. That's actually not the worst thing ever. So the last product that we did was this aldehyde and this methyl ester. And so now we're doing this thing, which I don't know why it looks so weird. Okay, so we're going to save this. This is 10. Does OpenBabel convert catcher files? Like, because my impression is that catcher files are probably the file format that is isomorphic to an actual drawing in catcher. And then presumably that has more information than the mole file. And so you could probably derive a mole file from catcher. And so I should just download the catcher and then use OpenBabel to convert to mole 3000 or whatever. Oh, so I didn't mean ChemDraw. I said catcher. Didn't I say catcher? Wait, didn't I say catcher? Okay, so we can't. So we got to do both, presumably. Both is probably the best thing. Okay, so did I save both here? Okay. Okay, now I gotta remember this Bichler nap. Dude, why doesn't middle mouse button pan? Like, literally every other drawing program in the planet. Wait, that's not what I wanted. I wanted Control Shift, Control P, Control Shift. Wait, Control Shift L. Ooh, now it's starting to look nice. Okay, good. Okay, so this is 11, and we want the ket file. Then we want 11. Fuck, that's so annoying. Okay. Okay, now all we have to do is because what happens? This lone pair goes warrant, warrant, warrant. Wait, no. Or if this is here. No, wait, something is definitely wrong. Bruh. Oh my god. How do you even fix this? I don't even know how you fix this. Is there like a mirror thing? Oh wait, actually I think but now we have this 5-member ring. Okay, that seems right. Wait a minute. This is wrong, dude. Oh, shit. This oxygen is supposed to be there. Bruh. I'm gonna start from scratch. I don't care. I'm gonna start from scratch. I'm getting good at this now. Oh, that's cool. All right, so we're gonna do Control P, Control Shift L. E. We actually wanted Z. How do I flip the stereo cam? Wait. Kind of like that. Ugh, I keep doing that. Yeah, it should be Z. Or actually, I don't think that's not really what I was going for, but actually, no, yeah, I don't want that. Okay, what if I did it now? Wait, did I just undo something? Okay, I don't know if that actually matters. You would assume it to be E. Okay, so save. So this is 1B. Get the kit format. Save. Save. 1B. Okay. Now I can do this. TTT. Boom. Boom. O. H. H. But I actually wonder about that. Like, can I? Okay, so you can. Oh, that's interesting. But they okay. All right. So I'm just gonna do it the way that I do it. My fucking god, I'm getting pissed. Oh my god, I'm getting... What? This isn't even selected. Help me. How did I select this? Oh, Jesus Christ. Help me out of this fucking shit, dude. But actually, I don't want this, dude. I want to fix this. Hmm. This is so painful, dude. This is actually so painful. Okay, we're good. This is what we wanted. Okay, this is two. Actually, the other two is fine. Wait. Ugh. Is this worth it? Actually, is this worth it? This is so painful. Shift 1 should whatever. It's not even worth it to complain. Um I'm a little bit confused about this step because it looks like methoxide, or rather just an alkoxide in general, is doing an SN2 reaction to substitute the bromine for a methyl ether. But the confusing thing to me is that the bromine was wedged or dashed. The bromine was dashed, and then the product of the SN2 reaction was dashed as well. Um, but that's confusing to me because if it was an SN2 reaction, we would expect inversion of stereochemistry there, right? Wait, did I say 7? Okay, so this is 6. Now this is 7. And 7 just oxidizes this. Okay, so this is 7. Oh my fucking god. I'm getting tired of this. Okay. Now here's the important part. This bond breaks. This bond breaks. This leaves. This forms a double bond. And similarly, this breaks. That's weird. Okay, so 1, 2, 3, 4, 5, 6, 7, 8. Okay, so we got 8. And I think this one's actually right now. I think this is where I started to go wrong last time. Oh, wow. Okay, so this does this. I'm going to just select all of this. So we still have these H's. We have this, this, um, no stereochem there. And then this becomes that. And then, wait, it's an O. Okay, I gotta be really careful here. So, 1, 2, 1, 2. Okay, so this oxidizes to an acetoxy group. This stays the methyl ether. This stays a methyl ester. This goes to methyl ester. This goes to methyl ester. This goes to aldehyde. So the only thing I need to fix is that this becomes Oh wait, this isn't right. This needs to be... Six, seven, eight, nine. The nitrogen substitutes in for this. And then I think it attacks this. And forms an amide. Oh, wow. Okay, so here's what happens. This mechanism is great. I'm actually not positive if this is exactly what happens. But what seems to me to happen is first, we form an amide. And then intramolecularly, we do a nucleophilic acyl substitution to replace the methyl with the amide or something. Dude, I have so much work to do. Holy cow. Okay, so first let me open up the so 6-methoxytryptamine. Wait, what? What? I thought I searched for this before and I found tryptamine. Okay, here's the smiles. So we're going to paste this in, but what I'm want to do is I'm going to take this whole thing and I'm going to flip it on its head like that. That's much better. Then I'm going to move this down here like that. Okay, and now here's what's going to happen. 1. Okay, so this is going to... oh, I need to do this. Okay. Did I get the one before it, though? Did I save this? Hopefully this doesn't have... okay, good. All right, so what I want to do is I want to open up a file. I'm going to go to source, chem, Moldros, data, reserpine molecules, try to 9.cat. Okay, so this is that. Okay, so good. So now I can do the next step and do 10. So 6, 7, 8, 9, 10. So what I'm going to do is I'm going to drag this into here. This gets 1. Then I'm going to tack this not directly to the O, but to the carbonyl. Okay, so this, yeah, right. So the nucleophilic acyl substitution, this is getting removed. This methoxy group is removed. So then presumably we're about there. So 1, 2, 3, 4, 5, 6. I don't know why the C is there. Oh, yeah, okay. Oh, the C is when the angle is small? I see. Okay. Makes sense. All right, so we're here right now. Okay, cool. So now I should be able to do P, oops, P, L. Bro, why does it make it so ugly? This is clearly a 6-membered ring. Why are you being so mean to me? I don't understand. But okay, I mean, whatever. The 3D is going to look good, so I don't actually care too much. As long as my stereochemistry is all right. So this is 10. So 10. All right, so we did 10. So now all I have to do is chlorine there. Okay. $11. A huge pain in the butt. Um. Oh wait. Oh shit. This is 10. Oh wait. This is 11. Okay, good. Now, can I just do that? Okay, good. I can do this. That looks beautiful, man. That looks really, really beautiful. Okay, good. So we've now drawn. This is all good. This is all good. This is all good. I got to get into the mechanism more. Definitely more mechanism. But in any case, we're going to save this as what? So 6, 10, 11, 12. All right, now 13. Let's see what happens here. So this is all the same. This is the same. This is the same, except this becomes a 1. And the H here becomes like that. And it's going to be interesting to look at the 3D model because I'm very curious to see like why. Well, I'm also going to have to read a lot more about like cuz the actual paper is like 1 page long. It's kind of insane how short it is. They don't really explain much of anything. And also, come on guys, why do they redraw it like this? This is so annoying. How the hell am I mapping this to this? Okay, so the carboxylic ester is here. So this carbon is that carbon. Why did they do this to me? Like, why did they do this to me? This is so cruel. Okay, so now what's the simplest way, or what's the best way to take either the mole file or the catcher output and get a 3D model? Okay, wait, so what is this? I'll just do the What just happened? Why is it fucking hidden? Why can't I see any? Oh, there we go. Oh, good. The fog of war. There's nothing like the fog of war. Yeah, I love that there's a fucking fog of war. Why do they have this? Who wants that? Yeah, let's make it dark as fuck so no one can. Alright, whatever. Alright, so. Okay. Okay, so this makes sense, right? Sort of. Where is that fun? So they're saying now it looks like this, right? So this is the methyl ester. So this carbon was this carbon. Why does it get dim? I don't like that. I don't see any purpose for doing that. Just sweep them with. No, maybe that's kind of how it's. Why is it taking up only a quarter of the screen, dude? Oh my god, bro. Alright, so we're gonna look at this head on, is what they're saying. And we have this chair. Right. This bond doesn't break and that bond doesn't break. So I should just be able to do... Oops. Delete. Delete. So that's this. So wait. 6, 10, 13. Did I ever do 13? This is 12. Wait, what was 13? Okay, wait. So let me undo. Okay, so this is 12. Now 13 is this thing. Where this is a wedge. This is 1. And this is that. All right, so I'm going to control P, control shift L. Save it. All right, slowly but surely I'm making progress. This is going to be so sick when it's done though. Is there a good review of this reserpine total synthesis? When I looked up the original paper, it looked like it was like 1.5 pages. It barely had any information on it. So I'm wondering if someone has like redone the Woodward synthesis that has yields for every step or something, or more information on what's happening in Woodward's original synthesis, because I'm having trouble understanding it. And I'm kind of surprised also that they were able to publish it with basically no info. Like, how did that happen? Okay. 14. So 14, all we have to do is actually delete this and delete this. Now, what's going on here? This is there. This is there. This presumably already has a hydrogen. Is it just a chair flip? $57? Oh, damn. Dude, the journal was called Tetrahedron. That's like so badass. mm, 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 mm. Or wait, I'm gonna go to source chem. Actually, I'll go to books, papers. Okay. All right. I'm gonna spend some. Okay. I'm gonna finish the drawings. Then I'm gonna read the paper. Did I mess this up? Wait, red, does red mean R? Wait, reserpine they remethylate this thing? Okay, wait, let me look at the steps. Oh, and then they go back. Of course, they go back to the other drawing. That's nice. Presumably, this is the step that flips this. Okay, so now this breaks open this cyclic ester or lactone. The lactonization forces the ring system into a conformation where epimerization at the marked center proceeds to give the natural isomer. I don't. I honestly do not understand the stereochemistry of this stuff. Okay, I'm gonna read. Try to read the paper. I think. For centuries, the Indian snake root Rauwolfa serpentina bent has enjoyed a favorable reputation in its habitat as a valuable medicinal agent. The problem of defining the scope of its utility in terms of modern Western medical standards was complicated by the fact that the plant produces a very large number of closely related alkaloids, of which those present in larger relative measure are not those with the more interesting physiological properties. Only 5 years ago, Schittler first isolated reserpine and demonstrated that this new alkaloid was largely responsible for the hypertensive activity associated with crude Rauwolfa extracts. This discovery and the remarkable effect which reserpine was subsequently found to exert upon the central nervous system rapidly won for the alkaloid an important place in the treatment of hypertensive nervous and mental disorders. Schittler and his colleagues took structural studies in hand at once and were soon able to propose for reserpine the structure Yohimbine. What is that? Okay. It's what? It's trimethoxy. Oh, and then this is just the ester part of it. Okay, so this should be like this. Oh, oh. Something like that. reserpine. Oh, wait. Wait, oh, I'm missing something. Uh, Here's the indole, and then here is an N. Okay, I think I got. Okay. Thus, it was early clear that reserpine is a member of the great alkaloidal group of which yohimbine is the prototype and oldest known member. There remained a stereochemical problem of no mean There remained a stereochemical problem of no mean dimensions and in view of the stereochemical abandon with which nature has constructed the members of the yohimbine group. At least 8 stereoisomers of yohimbine itself have so far been isolated from natural sources. Few clues were at hand. Test? Okay, good. But by summer of 1955, the SIBA group and a number of independent investigators as well had completed a series of elegant investigations which permitted the elaboration of the full structure for reserpine. The stage was now set for rational synthetic efforts. From the first, we looked upon the synthesis of reserpine as an exercise in stereochemistry. It will be noted that ring E of the alkaloid is the site of an unusually heavy concentration of asymmetry. Indeed, 5 of the 6 asymmetric carbon atoms present are there disposed in a single consecutive chain. Consequently, it are designed to construct first an assemblage of the type 3 with the 5 groups attached I don't even know what he's talking about. Indeed, 5 of the 6 asymmetric carbon atoms present are there disposed in a single consecutive chain. So, stereocenter all along here. Consequently, it was our design to construct first an assemblage of the type 3 with the 5 groups attached to the single cyclohexane ring suitably chosen in respect of function and properly oriented. It will be noted that the newly formed six-membered ring of the adduct was destined to become ring E of reserpine. That it contains already a felicitously, I don't even know what that means. At Okay. Aptly placed carboxyl group. A double bond of for the introduction of oxygen atoms at appropriate positions. And three asymmetric carbon atoms properly oriented. The well-known stereospecificity of the Diels-Alder reaction enabled us to assume with complete assurance that the two rings of the adduct were cis-locked. And that it was only slightly less certain that the hydrogen atom at the third of the asymmetric centers created in the addition reaction would be on the same side The well-known stereospecificity of the Diels-Alder reaction enabled us to assume with complete assurance that the two rings of the adduct were cis-locked, and it was only slightly less certain that the hydrogen atom at the third of the asymmetric centers created in the addition reaction would be on the same side of the molecular plane as those at the points of the ring juncture. Thus, the only known form of vinyl acrylic acid But I gotta reread this. I gotta get my footing. As you might remember from your general chemistry course, an atom consists of a dense, positively charged nucleus surrounded by a relatively large distance uh, of negatively charged electrons. The nucleus consists of subatomic particles of neutrons, which are electrically neutral, and protons, which are positively charged. Because an atom is neutral overall, the number of positive protons in the nucleus and the number of negative electrons surrounding the nucleus are the same. The solution to a wave equation is called a wave function or orbital and is denoted by psi. Mm. Oh, interesting. You get okay. So the number of orbitals is the number of independent angular wave functions. Whoa. Okay, I'm starting to see this functional analysis thing because look, psi is not just a vector in this case. Psi is a function. And so somehow we have eigenfunctions. So, hold on. E is presumably the matrix type thing or the linear transformation type thing. Let me try to remember my freaking linear algebra. Ax is equal to lambda x. X is a vector. This is a linear transformation. And this is a scalar. So in h hat, which I don't even know what that is, psi is equal to E psi. This is the eigenvalue. And what are we talking about, dude? I want to learn this stuff, man. Hamiltonian. This stuff is sick. I like this. I wish I knew it more. I bought the Griffiths book last night because I was like, dude, how am I gonna say that I'm a chemist if I don't understand anything about quantum mechanics? Like, dude, we talk about like we draw these little pictures and we're like, oh, these little lobes have to line up. Oh, but this lobe has to look like Come on. We need more powerful language. What wave functions psi are allowed? Okay, 1. Where do orbitals come from? You start with the Schrödinger equation for a stationary state. I don't know what that means. This is an eigenvalue equation. You're asking what wave functions psi are allowed such that applying the Hamiltonian gives the same function back, just multiplied by some number e. There isn't just one answer. There are many possible solutions with corresponding energies. This is completely analogous to a vibrating string having multiple... I need to remember my waves. Dude, I really wish I had gotten deeper into the physics because of the waves. But dude, my prof was like checked out, and that made me check out. It's my fault, but really, I could have done a better job. Um. Is it frequencies? So why do we... This is so weird. So why do we call it 1s2? Why don't we just say what the... Okay. They are different possible states of the same... Okay, wait, hold on. This is... Alright, let's go back to the eigenfunction thing. Alright, so you're asking what wave function psi, which means what wave function psi are allowed such that applying the Hamiltonian gives the same wave function back, just scaled by some number e. There isn't just one answer, there are many possible solutions. This is completely analogous to a vibrating string having multiple allowed standing wave modes. The same string can have fundamental mode, second harmonic, third harmonic. There are different possible states of the same physical system. An electron bound to a hydrogen nucleus can be in 1s, 2s, 2p, 3s, 3p, 3d. So when you ask, how can the same system have different wave functions? So is an orbital literally a wave function? For a one electron atom like hydrogen, bro, it pops out this equation way too quickly. Okay, it's some function of the distance to the nucleus, radial distance, times y, which is a function of its angle. But because of spherical symmetry, presumably this is a constant. I forgot. Is it always the case? Oh wait. What am I doing here? Oh yeah. I forgot. Is it always the case that the set of eigenvectors is a linearly independent set? Eigenvectors belonging to distinct eigenvalues are linearly independent. Yeah, because you could just scale the. Because, yeah, any. Yeah. Okay, well, that was interesting. Um. Hmm. Yeah, I'm gonna go walk around the. Oh yeah, well, I'm gonna walk around the block. Uh, dude, like that was a rabbit hole that I did not expect to go down. I don't really get like that reading that poly exclusion principle thing. It didn't really tell you why. I mean, like it just said here's how it is, but we're not gonna say why. Okay, so the Hamiltonian operator represents the total energy of the system. The Hamiltonian operator but it returns a function. How does the function tell you what the energy of the system is? Those are energy eigenfunctions. Okay. Oh, interesting. Okay. The eigenfunctions of the Hamiltonian operator can, under the usual quantum mechanical conditions, which I don't know what that is, form a basis for the space of possible wave functions. That means an arbitrary state can be written as a linear combination of energy eigenstates. Oh, things are clicking in my mind. That's very cool. A little bit of this and a little bit of that. I don't quite understand. So I understand that an operator is basically a function that takes a function and returns another function. And the Hamiltonian operator takes a wave function and returns a function that describes the energy. But I don't understand how, in a non eigenvalue, eigenvector case, how do you get the energy from the resulting application of the Hamiltonian operator to some arbitrary wave function? The Hamiltonian takes a wave function and returns another wave function like vector. Only when psi is an eigenfunction does the result reveal a single energy. For an arbitrary state, there may simply be no single definite energy. It just has to be. So basically, okay. So if you want to find the energy of some arbitrary wave function, you gotta first find the eigenbasis and then write it in terms of a linear combination of the eigenbasis. or the elements of the eigenbases. I kind of love this because it's like a lot of linear algebra. It's kind of fun. I love linear algebra, dude. Linear algebra is so sick. I'm not even that good at linear algebra, but it's great. What an amazing subject. All right, so I'm only there's only so much quantum mechanics I can learn right now. I guess I just really want to understand this reserpine Diels-Alder thing. Where's that other one that I downloaded? Hubei. All right, let me try to read this one because the other one is just a little bit too advanced for me, man. All right, reserpine is one of the lipid-soluble indole alkaloids sharing the yohimbe pentacyclic skeleton, yohimbine. Pharmacological studies have revealed that reserpine is a central nervous system depressant. It blocks the postganglionic nerve fiber from the excitatory neurotransmitter norepinephrine in the synaptic gap and depletes all of the biogenic monoamines, serotonin, and the catecholamines by inhibiting their accumulation in storage granules in the brain. intestine, platelets, and other organs. Because of its remarkable antihypertensive and sedative properties, it is still used today for treatment of hypertension and psychiatric disorders. Actually, you know what would be, it's a pretty good thing to do though, is it's insane to me, dude, that for real there isn't just like a little terminal down here. Get smiles, or like a command palette, smiles, copy smiles to clipboard. I'm not gonna get caught up on the tooling, but what I want to know is if I just open up another catcher. Ah, fuck you. So annoying. All right, and if I go to PubChem, and then I just load in, the problem is, do they do wedges and dashes in the drawing? They do. So these, um, so I'll be able to see if mine looks right. The main thing is that, okay, so this is ring E here, right? How do I zoom in, bruh? Oh my gosh. Alright, this is ring E. And the main thing is that see these. Well, what's weird is actually, wait, can we get a different conformer? Because the interesting thing is, look, this is di-equatorial, which is strange. Kind of wasn't expecting it to be di-equatorial. But here's those 5 stereo centers. And the main thing about these both being pointed down is that then the ring has to be, and actually what's weird here is that this is axial up, and this is equatorial up, right? Because this is equatorial down, and this is axial down. And so this ring here, that's why it's shaped like that. Think I'll make some food. What should I eat? Okay. But I guess what I'm wondering is if I copy the smiles. I'm actually curious to see even if this works. But if I just do this, bam. Oh, wow. I mean, this is not. Is this correct? How is it even getting that? Presumably this is right. Yeah, that's what I was thinking. That there's 6 stereo centers in reserpine. Okay, so here's the E ring. So A, B, C, D, E. So, okay. Strategy evolution, dude. This thing is sweet. Okay. The main sources of reserpine are in various Rauwolfia species. Reserpine has also been isolated from other closely related plants. Whoa, what the hell? The absolute stereochemistry of reserpine was proposed by Schittler and Dassey by the use of Klein's extension of Hudson's lactone rule to the molecular rotation difference between reserpic and reserpic lactone. Wow, I don't even know what that means. With the structure and stereochemistry of reserpine established, its biosynthetic origins were proposed. In 1960, Leet used radioactive tracers to prove that tryptamine is the precursor to the... Oh, what? Dude, I love those radioactive tracers. That's so cool. That tryptamine is the precursor to the indole moiety of reserpine. It is now believed that the initial steps in the biogenetic pathway of reserpine involve the oxidative cleavage of loganin to provide cycloganin. Cycloganin, upon coupling with the 6-methoxytryptamine, yields the indole alkaloid skeletal type that provides a vincoside, I don't know what that is, vincoside derivative with the correct reserpine stereochemistry. Structure-activity relationships studies have shown that while the C18 trimethoxybenzoyl group is necessary for the sedative activity of reserpine, the C17 methoxy group is not. Okay, so what? In addition, steric factors must play a role in its mode of action because this clue provides the synthetic chemist a starting point for modifying the skeleton of reserpine in a search for a more efficient antihypertensive agent that has fewer side effects. The degradation of reserpine can be achieved by 4 approaches. In the first approach, reserpine was heated in formic acid in the presence of formamide. Formamide. Oh, wow, wait, formamide. Is that just... Oh, yeah, formamide. This seems like a cool molecule. Dude, what I want to do is I want to do structure-activity relationships of freaking... the scent system, like looking at scent receptors and seeing like, can we design, make new scent experiences? Like that's kind of where I'm at, man. That seems like such a cool area of research, scent chemistry, because it's so immediate, man. All right, whatever. So I don't really care about that. Thus, the total synthesis of this alkaloid has been considered one of the historic yardsticks in the annals of natural product synthesis. In this regard, the first represented a milestone. Historically, two fundamental synthetic strategies have provided successful access to this yohimbine alkaloid. And these entries are depicted in a retrosynthetic format in Scheme 3 for illustrative purposes. The more widely employed E-ring strategy, following the original concept of Woodward's reserpines, focus on the primary synthesis of the E-ring portion of the molecule, followed by elaboration of the D, C, B, and A rings in ascending order. An alternative efficient DE ring strategy okay, whatever. To date, several outstanding reviews of the chemistry and synthesis of yohimbine alkaloids, including reserpine and other yohimbine alkaloids, have been published. So yohimbine, yohimbine's stereochemistry is different, however. If we were to look up yohimbine, it looks like the stereochemistry here is different. So if we were to then look at this, oh, see, look at that. Wow. See how much flatter it looks? This is still the E-ring, but look, because we have an anti-relationship between those hydrogens, or whatever, trans, that's interesting. Really, I think it's definitely the case that a lot of natural product synthesis challenges are stereochemical. That's becoming clear. The present review focuses on the total synthesis of reserpine, commences discussion with report of the first successful and okay. The first total synthesis of reserpine was achieved by Woodward only a year after the elucidation of its structure. It'd be like, that's crazy. If he did that in a year, and then think about how hard vitamin B12 was. This seminal synthesis began with a brilliant stereoselective construction of the stereochemically and functionally rich E-ring, followed by condensation with the tryptophyll subunit and subsequent C-ring closure to elaborate the pentacyclic reserpine framework. It concluded with a cleverly executed epimerization at C3 to create the correct 3 beta H stereochemistry of reserpine. What is epimerization? I don't even know what that means. Epi is like above, right? Oh, epimers are stereoisomers that differ at exactly one stereocenter. Dude, I feel like I would love the combinatorics of like epimers. Like how do we flip any one that we want? That's really cool stuff. Falling, dreaming, talking, and only I know you want to all night. Don't you grow up in a hurry. Yo, my mommy worry, oh, it went out on a story. An alkaloid is just a natural. Wait. An alkaloid, a broad class of naturally occurring organic compounds that contain at least one nitrogen atom. Yeah, so it's literally just. Um, alkaloids are naturally occurring, nitrogen containing, and usually basic secondary metabolites. Okay. Ah, interesting. A secondary metabolite is a molecule an organism makes that is not directly required for the basic processes of staying alive and growing, but instead serves uh, more specialized ecological or biological roles. Got it. Okay, cool. Where are we at here? Reserpine. This is a great this is a great project because it's like, how do you look at a single molecule for so long? You have to just do it. You have to just do it. And you learn things. And that's the part about this. Um Woodward's work laid a foundation for many future syntheses of reserpine because the synthesis of many of the intermediates developed in their approach have been attempted by different groups. Woodward's synthesis outlined in Scheme 4 um, do they have yields actually on theirs? Where is theirs? Books, papers, reserpine. Wait, where's the original one? Oh. Uh, I'm thinking of making a short website that is an overview of the presentation, just for my own sake, not for our project, just to like get on solid ground. Books, papers, reserpine. Okay, so in the original Woodward paper, does he provide actual yield percentages for each of the steps? And if not, how can I obtain that? But they're working in huge quantities. Why were they doing such massive quantities? Okay, I gotta stay focused because there's a lot of information and this is quite challenging actually. Woodward synthesis outlined in scheme 4 commenced with an intermolecular Diels-Alder reaction between 1,4-benzoquinone and vinyl acrylic acid via the endo transition state. Uh, should I go on YouTube?
In this Layer for Sci video, we're going to look at the stereochemistry of the Diels-Alder reaction. In previous videos, we looked at the Diels-Alder reaction mechanism and a shortcut for quickly identifying products. The problem is, everything was flat. If you take a look at this reaction, we have a diene with two substituents, a dienophile with two substituents, and the product drawn with no stereochemistry. This is acceptable for the starting molecules because this carbon and this carbon on the diene are both sp2 hybridized, that means they're trigonal planar or flat, as well as the dienophile. Again, sp2 and sp2 hybridized, trigonal planar, and flat. Let's quickly number the molecule. We have 1, 2, 3, 4, A and B. This is the trig I teach in the previous videos, which you can find on my website link below or by visiting layerforsci.com/Diels-Alder. If we now look at the product with the same numbering scheme, you'll notice that the substituent on carbon 1, carbon 4, A and B are all sitting on sp3 hybridized carbons. sp3 is tetrahedral or three-dimensional, and that means the substituents have to go up and out of the page or down and into the page, and the question is which one. Let's start with the stereochemistry of diene. If I have a substituent coming out of carbon 2 or carbon 3, we don't have to worry about it. Why not? Both the starting diene and the cyclohexene product have the substituents sitting on an sp2 carbon. It started out flat, it ended flat, and so the substituent is still on the plane of the page. No stereochemistry.
Wow, she's good at
This
explaining,
means that the
dude.
substituent sits on carbon 1 or 4.
Dude, really, this is a great explanation.
Hybridized, one substituent will point straight up and on carbon 4 straight down. The second substituent would point inward, down on carbon 1, up on carbon 4. Let's call the outside substituents A and the inside substituents B. We'll react with a simple dienophile to give a product that looks like this. If the substituent is outside, that means it's pointing straight up or straight down, then the substituent goes on dashes into the page. If the substituent is inside, our product will be on a wedge coming up and out of the page. This used to confuse me, and so I like to think of it as follows. The inside substituents are close together, and so we want to bring them closer. How do we bring them closer? By drawing them up and out of the page, they're coming directly at me, closer to me. The outside substituents are further apart, and so we push them away. How? By pushing them down and into the page. This works even if your starting molecule is a ring, such as the cyclopentadiene. Notice that the ring counts as my inside substituents, and hydrogen will count as the outside. And so for our product, we start with our cyclohexene. The starting molecule is 1, 2, 3, 4, with carbon 5 as the tip that we're going to draw upward the way I taught you in the previous video. Upward, because it's the inside substituent, and so they're close together. We bring them closer, up and out of the page. And while you don't have to show hydrogens for the sake of stereochemistry, I'm going to draw them down because they're further away, and so we push them further down into the page. You can also draw your cyclohexene as a breadbasket, with carbon 5 coming up and out of the page, and the hydrogen, which is typically invisible, down and into the page. Now let's take a look at the dienophile stereochemistry, specifically endo and exo. Starting with a simple molecule that has an aldehyde substituent, to give me the following product. If I draw cyclohexene, I have an option of putting the aldehyde group coming up and out of the page, or going down and into the page. The convention for this comes from having ring substituents, but we'll simplify it here to say that if it's coming up and out of the page, this is the exo substituent, and the way I think of it is that it's exiting up, out of the page. If it's going down and into the page, I think of it as the endo substituent because it enters into the page, endo going in and exo coming up and out. Now what happens if I have two substituents on my dienophile, such as two aldehydes in opposite or trans configuration, or two aldehydes in the same or cis configuration? The cis and trans stereochemistry will be retained, and once again I have the option of drawing it two different ways. For the trans option, I can put the upper aldehyde out and the lower one in, or the opposite.
I think I'm coming to the conclusion that there's gonna be only so much I can do here. But I gotta get this, but like is this the speed or not? Oh, but it resets the visualization. That's kind of annoying. See, this is what's kind of weird to me though, is like I don't really get what it is though.
Giving me two different products that in this case are enantiomers of each other. Be careful though, they're not always enantiomers. If I add a methyl group here, now the two products become diastereomers. And I challenge you to figure out why that changes. Same thing for the cis configuration, the product will still be cis, and so I have the option of bringing both of the groups up and out of the page, or both of the groups down and into or into the page. Since both substituents go in the same direction, when they come up and out of the page or exit the page, we get the exo, and when they go down and into or into the page, we get endo. For even more on the Diels-Alder reaction, including the tricks and shortcuts that I mentioned.
So I wonder where that guy. Where's that Journal Club one? That Journal Club one was actually pretty good. Wait, what are the Woodward Hoffman rules? It's rules for pericyclics. Okay, I think I might move upstairs soon. I'm getting cold. Okay, I'm just gonna do it. I'm getting cold. All right. Okay. Um, let's see where are we at here. Okay. Oh my god. Okay. All right. Good. Dude, vitamin B12 is nuts. What do the red and green dots mean? But did the colors red and green actually mean anything? Because I feel like I saw something about there's a meaning to them, to the colors, but I don't know. Okay, fair enough. Okay, let me see if I have this structure memorized, because I'm pretty sure I have it memorized. Yeah, bro, I got it memorized. Okay, so the main steps retrosynthetically, we're
earlier, visit my website link below or go to layforsi.com/dealsolder. Again, that's layforsi.com/dealsolder. For even more on organic chemistry, including Leia here from layforsi.com, and in this video, I'll show you the Diels-Alder reaction mechanism and then a quick trick to help you find the products without going through the mechanism and to help you find the starting molecules when you're given a product. You can find my entire Diels-Alder series along with a reaction guide and practice set by visiting my website layforsi.com/dealsolder. A Diels-Alder reaction is a concerted mechanism for a cycloaddition reaction. The Diels-Alder reaction happens when you have a diene and a dienophile reacting with just heat to form a cyclohexene. So let's break it down. The first thing we have is the diene. More specifically, this has to be a conjugated diene where the pi bonds are directly near each other. There are two forms that you'll see for the diene. The first form is called the S-trans, and that's
oh yeah, I forgot about this actually. I forgot that there was a name for it.
Looking like a transalkene, except that instead of a pi bond with the two substituents coming out, you actually have the diene set up in the trans position, but there's a single bond between the two pi bound groups. But this is still significant because even though this bond here is technically capable of rotation, don't forget that in a conjugated system you do have resonance. And when you have the pi bond resonating, that locks the molecule into the S-trans system.
Really? I mean, I guess.
In order to do the Diels-Alder reaction, you have to have the S-cis system, which should remind you of a regular cis molecule where you have a pi bond and then the two substituents are attached on the same side. The S-cis is slightly less stable because the groups are too close to each other and that will raise the energy of the molecule. In order to convert from the S-trans to the S-cis, you need some heat. The heat will destabilize the molecule, interrupt the resonance enough to allow for that rotation to happen. But that works out nicely because the Diels-Alder requires heat for the mechanism anyway, so as long as the molecule is capable of rotation, the heat will help turn an S-trans into an S-cis. The next thing we have is a dienophile, which as the name implies, diene, loving. So if we have a diene, then the dienophile likes the diene and wants to react. This is the very simple form of the diene and dienophile, but typically you'll see the diene with electron donating groups making it very electron rich, and the dienophile with electron withdrawing groups making it electron poor, and that helps the two molecules come together and helps them want to react. This type of reaction is called a cycloaddition because it's a cyclic addition. We're forming a ring, and it's called a concerted mechanism because even though we draw the arrows individually, they all move at the very same time. To show this reaction, we'll start with one of the pi bonds on the diene and show it attacking the dienophile. And what we're doing here is actually forming a bond between the diene and the dienophile. So those purple electrons that used to be a pi bond now form a sigma bond. That means the carbon on the dienophile has too many bonds, so its pi bond is going to get kicked out, and that will form a bond between itself and the other end of the diene, which means that this bond has to move because we have too many bonds on the lower carbon.
So this thing has a lot of electron density. This has no electron density, so that's why it's attacking.
And that forms a pi bond between the two carbons that used to be part of the different pi bonds. The transition state of this molecule sort of looks like the resonance happening in a benzene ring, because notice this looks like benzene with the 3 moving pi bonds, and this is what you would see. These purple electrons are moving over. The blue electrons are moving over, both of them starting as a pi bond, winding up as a sigma bond, and then this pi bond moves over and is still a pi bond. So you kind of see a circle of resonating electrons inside the diene and the dienophile. And the product is as follows. The former purple pi bond is now a sigma bond between the diene and dienophile. The former blue pi bond is also a sigma between the two molecules. And the former green pi bond now sits as a pi one position over, giving us the final product as a cyclohexene. Now, many of the reactions you see will have more complex molecules, but if you can identify the position of that cyclohexene, you'll be able to put the pieces together for everything else. And that's the key. If you can recognize the pattern, and you can take your complex molecules and simplify it into the form that you see here, the entire complex reaction suddenly becomes very easy. And here's what you want to recognize. No matter what is on your diene, you want to identify the 4 carbons as follows. 1, 2, 3, and 4 represent the 4 carbons that form the diene, where 1 and 2 is the first pi bond and 3 and 4 is the second pi bond. Reacting with that, we have the dienophile, which we'll label A and B. For the product, the pi bond moves over, so it's always going to wind up between carbons 2 and carbon 3, and that's how you identify where to start numbering. We have 1, 2, 3, and 4 connected to A and B. That's the pattern, 1, 2, 3, 4, A, B, in a ring with a pi bond between 2 and 3. Before we take this trick further, I want to show you how to recognize the product without showing all the arrows. I want you to repeat after me. Break, make, break, make, break, make. Got it? Watch. Break a pi bond, make a pi bond. Break a pi bond, make a single bond. Break a pi bond, make a single bond.
How is that any more helpful?
And that will be a little key that will... So we'll go back to the pattern, shrink that down, and that will be a little key that we'll use as a trick for solving more complex molecules. And again, we're always going to look for the pattern. So let's say you find yourself faced with a molecule that looks like this. We have 6 carbons in a chain with 2 pi bonds. We have our diene, and it's in the S-trans position. And we want to react that with a molecule that has a pi bond and a carbonyl at the end. First, we want to know what's our diene and what's our dienophile. The diene tends to have electron donating groups, making it more likely to attack something. Methyl groups on either end of the diene qualifies as the electron donating groups. And the dienophile wants to have electron withdrawing groups. If you have a carbonyl capable of resonating onto the oxygen atom, the carbon of the carbonyl is going to have its electrons pulled away, making that partially positive. That means the electron withdrawing group makes the dienophile partially positive, making this an ideal reaction. So here's what we're going to do. We'll take our starting molecule and set it up just like we have the key, where the diene faces the right side of the page, and we plug that in. That's what we're starting with, not the entire molecule, just the diene, and then we number 1, 2, 3, 4. Once we have the numbering in, we fill in what's left. We have a methyl group on carbon 1 and a methyl group on carbon 4. We'll do the same thing for the dienophile, starting with a pi bond for A and B, like we see over there. So we have A and B. Attached to it, we have a carbonyl, and in this case, it doesn't matter top or bottom because this molecule is symmetrical. In a later video, I'll show you how to take into account the stereochemistry and how to set up asymmetrical molecules. So randomly attached to B, I'll put the aldehyde, and we're ready to go. We put the reaction arrow with heat. Now here's the best part. I don't want to look at my starting molecule when I come up with a product because the starting molecule has substituents which will just confuse me. Instead, I go to my little key and draw a cyclohexene. Once I have the cyclohexene, I'll fill in the numbers. 1, 2, 3, and 4, because the pi bond's always between 2 and 3, followed by A and B giving me the ring. We have the starting product, and now we look back at the starting molecule. Carbons 1 and 4 both have methyl groups, so we give them their groups. A and B have an aldehyde attached at B, so we'll put the group right there, and here's our product. Again, in this reaction, we're not showing stereochemistry because I want you to focus specifically on the trick. Now let's say you're given a product, and you're asked to find the starting diene and dienophile that gave you this product. Once again, we're going to refer to our little key and use that as a trick to identify what's going on. We're looking for a cyclohexane with a pi bond between 2 and 3. Our molecule has a 6-membered ring, but there are 2 pi bonds. How do you know which is which? We have to analyze each pi bond and determine if it has an electron donating or withdrawing groups, and recognize that the diene has electron donating groups and the dienophile would have electron withdrawing groups. We have 2 esters on the pi bond on the right. Esters have carbonyl carbons, which when they resonate are partially positive, making them electron withdrawing, and that means the one on the right is more likely part of the dienophile and not the diene. So we know the pi bond on the left has to be from the starting diene, and we'll number accordingly. 1, 2, 3, 4, A and B. Remember the pattern I showed you of break, make, break, make, break, make? We're going to do the exact same thing here, starting by breaking the pi bond between carbons 2 and 3, because we know that has to move. So we break a bond, make a bond, break a bond, make a bond, break a bond, and make a bond. Notice that because we already had 1 pi bond, A and B will actually come from an alkyne, because the Diels-Alder reaction only breaks 1 pi bond, so if we start with a triple bond and break 1, we still have a double bond in the product. Another way to recognize this is that you have to cut between 4 and A and B and 1, because 1, 2, 3, 4 is part of the diene, A and B is part of your dienophile. So we'll start with the diene. All we have is 1, 2, 3, and 4, nothing else. So I have a standard starting molecule. For the dienophile, we'll start with A and B. Recognize that we have to put 2 bonds for the alkyne, and then we have an ethyl ester on either end, so we'll just add that in here. And these are our starting molecules. So now what happens if your starting molecule has a ring in it, or worse, your ending product is a bicyclic compound? How do you treat it then? That's exactly what we'll look at in the next video, which you can find along with the Diels-Alder reaction guide and practice problem set by visiting my website, leahforsci.com/Diels-Alder. Leah here from leahforsci.com, and in this video, we'll continue the Diels-Alder reaction. I also used a molecule that was oriented differently and made it fit that trick. But what if I tell you that you're starting with 2 molecules of 1,3-cyclopentadiene and reacting it with heat to form a Diels-Alder product? How do we make the ring fit that little trick, that little key here? Well, organic chemistry is not an art class. It may feel that way, but as long as you draw your molecule correctly, it doesn't have to be pretty. So to start my reaction, I always want to start with a pattern of 1, 2, 3, 4 for the diene. And remember, it's not an art class, so if I close the ring over here and put that as position 5, that's fine, right? But what if my drawing is a little off and I exaggerate it and put it over there? Is that still correct? Yes, it's not drawn very pretty, but it's correct. What if I now take carbon 5 and put it all the way up here? It doesn't look right, but as long as carbon 5 is attached to carbon 1 and to carbon 4, it's technically correct. Now recognize the bonds can bend that way because carbons 1 and 4 are sp2 hybridized, meaning they're trigonal planar and flat. But for the sake of this reaction, I'm just drawing it out of the way. I'm exaggerating it so that I can make my diene look like the standard form. For the dienophile, I can rotate the molecule so that I use either of the two pi bonds. It doesn't matter because we have a symmetrical starting molecule. So when I set it up, I make one of the pi bonds face the diene and label that A and B. Add some heat to get the reaction going, and that's it. Now remember I showed you that you cover your starting molecules. You don't want to get confused by all those bonds. Instead, you want your starting molecules to get the reaction.
Oh, shoot. Oh. Okay. All right. So what's happening here? I totally forgot. Okay, so we can actually do this like Diels Alder like cyclization thing. Okay, so the diene. Ah, ah. There we go. Okay, so it goes like this. But then this could undergo. Yeah, dude, you could pull like cool Diels Alder polymerization. Is it possible to get like Diels Alder polymerization things? Like if we just took like uh well, I don't know if benzene would do it, but maybe like 1,3-cyclopentadiene or something. Like could we just get more and more rings? Oh, okay. Oh, what? That's not even worth it then. Wait, is it worth it? I can't even remember. Nah, it's not worth it. Hold on. When your Chipotle has a 1.5 stars. Okay. Um. What is a click reaction? Where did he work after 1990? He won the Nobel Prize twice, dude. Stereochemists. Dude, chemistry is like the thing is it's so deep. Or it's like it's so vast. I think that's kind of maybe what I'm like.
Action going, and that's it. Now remember I showed you that you cover your starting molecules. You don't
All
want to
right.
get confused.
I don't really know how to explain this thing, but I gotta finish. Where are we at with this? Where is all my um catcher? Okay, so uh Okay, so I need to pull up the reserpine synthesis paper. Okay, here we go. Okay, so what step am I at? I'm at 6, 10, 13. Oh yeah, now see, now I'm stuck on this thing. Um, I'm not really sure. I think this hydrogen is still down with respect to this. But honestly, I can't really tell. But okay, so I believe that this is. Wait, oh wait. Did I ever ask like what is going on in this step? Okay. You have a question? Wait, what? What is it saying? Dude, it's making this up. Okay, I'm gonna say that 14. Uh, wait, hold on. 6, 10, 13, 14. Um, wait, hold on. If I do, is this 13? All right, so here's the E ring. What is it called? Acetoxy, methoxy, methyl ester. Okay, good. So there's that. Then there's this, which is OH or me, COOH, indole. Okay, I think that this is right. So this is 14. Get the ket format. That's the best format. We save the mole format because nothing besides catcher actually does this. This is 14. Okay, good. So now 15 I'm skipping. I skipped 15. I think it's the same. So then here what happens is this presumably comes in here to do that. Wait, what? What just happened here? That's not what I wanted. What I wanted was this gets, oh my gosh, I didn't even select that. Okay, and then this goes under there. Is that right? I don't think that's right. That's definitely not right. Wait, oh no, because, wait, this is a carbon. Oh, I see what's happening. Okay, wait. No, no. What am I doing? Oh, I get it. Okay, this is what's happening. This thing's pissing me off, dude. Okay, something like this. Okay, so this is 16. So first I'm going to do Control P, Control Shift L. Please don't mess with me. Okay. Save. All right, now we have 16. Okay, and now something weird happens where this does that. And I don't know how the heck that really happens, but apparently that happens. Oh, I'm not signed in, am I? Dude, it always signs me out. What? What? It's good stuff. Ooh, 500 grams, dude. Wow. It's a good deal. Okay. So, all right. So did I save that? This is 16. This is 17. Okay, I don't think it. Okay. Now we are adding sodium methoxide and methanol. And what's happening here is this thing breaks out, but it becomes a methyl ester. So we're gonna delete this, bring this back over like this. It's not an aldehyde anymore, but it's what? Dude, I swear this thing is driving me absolutely insane. Okay, good. So now we have we're pretty close. Oh, I hate this program. So this is 18. Okay, and now all I want to do is I want to get just do it like this. This will be faster, I think. So it's gonna be 3,4,5 trimethoxy benzoyl chloride. Smile. Smile. Okay, so here, here, this. That's good. And then all we want to do is and that's it. That is the last step. So this is so 6, 10, 13, 16, 17, 18, 19. So first off, Control P, Control Shift L. Save. So this is 16, 17, 18, 19. Wait, first the cat. All right, cool. I think this is it. Um, so I think what I want to do actually is, um, so what I want to do this. Let me see if this works. Okay, so what I want this project to be is a small static website on GitHub pages that has basically is a slideshow that has both the 2D and 3D drawings of all of the intermediates in the Woodward's reserpine synthesis. Now I've manually gone ahead and drawn all of them in Catcher, and I've exported them both in the Catcher file format and in the mol v3000 format. I've done my best to do the stereochemistry correctly, and the thing is, the Catcher files and the mol files don't have proper 3D coordinates, so you will have to do some of that to make that work properly. But I drew it all, and it took me a long time, so I feel like you can take it home, and I'd like to see the result. Oh, good. I was worried that that was not going to. I thought that was not working. I'm glad that I have dictation now. That's great. It always does so much extra prep work. I don't really know why it does all this. Oh wait, did I never export mole files for the? I don't think that's accurate. Source, chem, reserpine, data. Oh damn. Uh, what the hell are you doing, boy? What the hell is it doing, dude? Okay, once I have a first pass, then I can start to do the rest. Catcher's not bad. I don't hate catcher. It's just like pretty bad. Oh, is it grinding compute at this point? Okay. So once Open Babel generates the 3D, I want to see how close it is to this.
This is going to be a long journey, but if you stick with me,
Dude, no way. What the hell? It's slow. Hurry up. It's so slow. Yeah, I want to try this again on um oh, now I can probably have an AI help me do it properly because at the time I didn't know if I was using AlphaFold correctly, but I always wanted to know, can we use these protein structure prediction models to understand like sickle cell anemia specifically? Because that's one of those ones where it's a SNP, but it's a hugely impactful SNP all around the world. What would be interesting too is closing the loop on using automated labs obviously to validate hard spaces of this where the model has no training data or has very low confidence predictions. Because that would be so cool. A fully automated like crystallization and everything. Oh my god, that'd be so sick. In the report, we demonstrate through several examples that we can successfully model complex out distribution events, such as induced fits, where okay. Bro, can we clean up these drawings? Holy fuck. But this looks great, dude. This is right. Um, I think this is right. Wait, is this right? Yeah, because this is the methyl ester here. Dude, this is freaking cool, man. I actually like how this looks. Graphically, this is very beautiful. I think this is pretty ugly, but I don't care. All right, cool. That was sick.